paper we're diving into today is DHE Fusion Reactor Control Concept, Jeff W. A mouthful, I know, but it's actually a pretty fascinating in how we operate reactors using deuterium and helium-3, so-called DHE fuel cycle.
Yeah, right at the on of the paper is a question. Instead of asking, can you reach ignition, that is, can we turn the reaction on, it flips it into, can we stay in ignition? That's a big shift.
Exactly, because fusion isn't just about lighting the fire, it's about keeping it burning in a really messy, changing environment. The paper basically asks, how do you keep all these physics in real time, so you never drop out of that sweet spot where fusion keeps going?
Answer is this thing called a control barrier function, which sounds like kind math and intimidating, but it's really about making sure the machine, at every moment, doesn't cross over into a zone where fusion fails. So you've got a line, well, it's a surface in this case, and as long as you stay above it, fusion's viable.
You know, I actually kind of pictured this as walking on mountain ridge in a storm. You can slip way if you're not careful. But the barrier function is like an automatic system that keeps nudging you back to safe zone.
I like that image. So how does it work in practice? The paper breaks it down. You've got sensors in the reactor measuring stuff like fuel density, plasma confinement time, all the things that together govern fusion is happening. These are folded together into a viability function, and as it's positive, you're igniting. If it's negative, you're not.
Right. And to keep that function positive, the reactor uses a whole bunch of actuators, knobs to turn, heaters to fire, fueling valves, magnetic coils for shaping That's actually a lot of levers to pull, all at once. But you don't want to be yanking them all randomly, obviously. The heart of the paper is an optimization setup, how you change everything, but with the least effort?
They use something called a quadratic program, QP. Basically tells the actuators, do whatever need to, but don't overdo it.
I thought it was clever how the control system has modes. Like, if you're well in the safe region, it goes easy on the controls and just maintains things. But if things start to slip, it can get aggressive, pumping in more fuel, ramping up heating. And if stuff really goes sideways, it has a safe fallback mode to protect the machine.
Which, it's kind of like the safety features in a car. I know that's maybe stretching it, but if you start skidding on ice, the car takes over with all these control systems.
No, I think that actually fits. We don't let the driver, the operator in this case, micromanage everything when milliseconds count. The system sort of autopilots itself back to safety.
So, stepping back, what does this mean, right? I think it shows we're getting closer to not just can fusion work in a lab, but can we keep it running in the real world? It's a reminder, truth isn't ever finished. Papers like this move us forward, but they're part of an ongoing process. For anyone listening who dreams a clean energy future, this kind of work is what turns fusion from a science experiment into an energy solution, one crafted algorithm at a time. Little steps, or maybe little nudges along the mountain ridge, right?